Last time we started talking about, so the big topic that we're moving into, the overall topic is kinetics of rigid bodies in 3D. And a big part of that is the new complexity that goes with moments of inertia when you start doing things in 3D. And in order to talk about the mass moments of inertia, we needed a mathematical preliminary. And that was rotation matrices. So we finished talking about that last time. And so now we can start talking about what happens to the mass moments of inertia in 3D. Okay, so we go from being able to treat the mass moment of inertia like it's a scalar value to having to treat it as a 3 by 3 matrix. And it looks like this. The mass moment of inertia about a point is equal to an element that I'll call capital IX, then negative capital IXY, negative capital IXZ. And it's a symmetric matrix, which means this has to be negative IXY. The diagonals are IX, IY, and IZ. And then the off diagonals, so this one would be negative IYZ. Symmetric says that this is negative IXZ, and this is negative IYZ. Okay, so now you got this thing. And it looks sort of cool, but we need a way to calculate those values. So IX is, so the integral definitions. Again, we're not going to use these really, but these are the definitions of what these elements mean. IX is what you've seen before for the scalar definition. So it's the integral of y squared plus z squared dm. IY is the integral x squared plus z squared quantity dm. IZ is the integral x squared plus y squared dm. These are all familiar. But now we have the new ones. These are called the products of inertia. And they're defined this way. IXY is the integral of x times y dm. IXZ is the integral xz dm. And IYZ is the integral yz dm. These are new. We haven't seen these before. Now it's sort of a surprising fact that for every body, no matter how weird the shape is or whatever, it doesn't have to have any lines of symmetry or anything. for every body, there's a coordinate system orientation where the moment of inertia about the body's center of mass only has diagonal elements. And the coordinate system where this is true, those coordinate axes are called the principal axes. So this looks sort of familiar to some stuff that we've been doing in D-form. The people are taking D-form too. How would you guess? So say you're given this random, the computer calculation spits out some random expression for the moment of inertia matrix with values in every position. How would you imagine that you would come up with the principal mass moment of inertia? Yeah, it's an eigenvalue problem, just like it is for a stress tensor. And in fact, the moment of inertia matrix is also a tensor. It has the rotational properties that a tensor requires. Okay, here's a slightly harder one. What are the properties? So these principal axes always, the principal mass moment of inertia, these are always real values. It doesn't make any sense to have complex values for moments of inertia. What is it about this mass moment of inertia matrix that guarantees that we're going to have real principal moments of inertia? What kind of matrix has what kind of matrix has real eigenvalues? Symmetric, yep. The symmetry of that matrix is the key to that. Okay, so I'm going to give you these three common shapes that we're going to deal with. I'm going to give you the mass moments of inertia for those in 3D. And notice that it's really just a new formatting for the information that we had about these three shapes before. So here are the three shapes we'll use. The first one is a slender rod. Oh, like a couple days ago? Okay, let me give them again, and let me put it in the matrix format. Okay, so call that the y-axis. Call that the z-axis. And call that the x-axis. Then in the 2D formatting, we said that the moment of inertia about x was equal to 0. The moments of inertia about y and z were the same, and those are equal to 1/12 ml squared. So in the tensor format, we can write this as the mass moment of inertia about the center of mass is equal to 0, 0, 0. Then 0, the y element is 1/12 ml squared. And then 0 is until you get to the z diagonal element, and that's 1/12 ml squared. The second one is the thin rectangular plate. So let's say that this is the y-axis again, this is the z-axis, and this is the x-axis. The moments of inertia for that, if this distance is L, this distance is W, then the moment of inertia about x is 1/12 times the mass times L squared plus W squared. Iy is equal to 1/12 m L squared, and Iz is equal to 1/12 m W squared. And so you can write this in the tensor format. So the mass moment of inertia about the center of mass is equal to the x diagonal element is 1/12 m times the quantity L squared plus W squared. The y diagonal element is 1/12 m L squared, and the z diagonal element is 1/12 m W squared. And then the last one is the thin disk. So that's Y, that's Z, and that's X. The moment of inertia about X is equal to 1/2 mr squared, and then Y and Z are the same. Those are 1/4 mr squared. And so as a tensor, the moment of inertia about the center of mass is in the x position 1/2 mr squared. In the y position, diagonal position, 1/4 mr squared. And in the z position, 1/4 mr squared. Okay, so notice that for these shapes at least, finding the mass moment of inertia about the center of mass in the principal coordinate system is easy. Okay, what's going to take a little more thinking, a little more effort, is going from the mass moment of inertia about the center of mass in the principal coordinate system to mass moments of inertia about other points and with the axes oriented in different ways. Okay? So it will take more work to express the mass moment of inertia matrix first about points besides the center of mass, and second in coordinate systems other than the principal coordinate system. Okay, so the first one of these that we're going to talk about is how to calculate the mass moment of inertia. So first, calculating the mass moment of inertia about a point A where A isn't the center of mass, but the coordinate system axes are still principal. So let x bar, y bar, and z bar be the coordinates of the object's center of mass expressed in the new coordinate system. So like if you're trying to find yep. So if this is the center of mass and you're trying to find the moment of inertia, say these are the principal axes, and you're trying to find the moment of inertia about this point A, then x bar, y bar, and z bar give you the location of this in terms of this coordinate system. Okay. Then the moment of inertia about A is equal to the moment of inertia about the center of mass plus this new matrix that's equal to m times x bar squared plus y bar squared m x bar y bar m x bar z bar. It's symmetric, so this is x bar y bar. Then on the diagonal, m. Ooh, I did. Sorry about. We have to change one thing here. These should be. So we're trying to find. This works just like the parallel axis theorem in 2 dimensions. We're trying to find the distance from the old x-axis to the new x-axis. So this really needs to be y bar squared plus z bar squared. Then for y, this needs to be m times the quantity x bar squared plus z bar squared. And then m y bar z bar. Symmetric gives you these 2 elements. And then the last one is m times x bar squared plus y bar squared. That's the parallel axis theorem for matrices. For the moment of inertia tensor. And to add these matrices, you just add element by element. So add the 1, 1 element of the moment of inertia about the center of mass to this value, and that's your new 1, 1 element. add the 1, 2 element of this to this value, that's your new 1, 2. So just do it element by element. Anyone have any questions about that yet? Okay, so let's say, as an example, we have just some random blob, and this is the principal coordinate system, and now we have this new coordinate system A that's aligned with the first one. And say that we don't know anything about this shape, but we're given that the moment of inertia about the center of mass is equal to 5, -1, 0, -1. Okay, so this is not necessarily the principal. I mean, it's definitely not the principal coordinate system, but it is centered at the center of mass. So -1, 2, 2, 0, 2, 3. And say that we're given that x bar, y bar, z bar is equal to 0.5, 1, -0.2, and the mass of the object is equal to 1 kilogram. So where does a vector, this vector 0.5, 1, -2, that doesn't really line up with the axes, but what does that vector look like? Where's that vector starting and where's it ending? So the x bar, y bar, z bar, those are the coordinates of the center of mass of the body expressed in the new coordinate system. Okay, so that's a vector going like this. And we want to calculate the moment of inertia about A. Well, the moment of inertia about A is equal to the moment of inertia about the center of mass plus this matrix so for I guess let me write these values out. So the first one is mass times y bar squared plus z bar squared. The second one is mass times x bar y bar. The third one is mass times x bar z bar. This is symmetric, so all we have to do is the first half of this matrix, and all these come from the symmetry. So what's the YY element? Mass times x bar squared plus z bar squared. Then the YZ element is mass times y bar z bar. And then the last one we need is the third diagonal. That's the mass times x bar squared plus y bar squared. So let's fill in these elements using what we know. So what's mass times y bar squared plus z bar squared? How do you calculate that? Yeah, yeah, right. These values, these are x bar, y bar, z bar. We're going to plug those into this formula. We get, let's see, I think 1.04 for this one. 0.5 for this one. For this one, we get negative 0.1. Then symmetry. For the y diagonal, we get 0.29. For yz, we get negative 0.2. And then we know some things from symmetry. And then the z diagonal, we get 1.25. And so the total moment of inertia we get from adding up these elements with these elements, and we get 6.04, 1.5, negative 0.1, 1.5 from the symmetry. The y diagonal is 2.29. YZ is negative 2.2. Then we have symmetry, and the z diagonal is 4.25. Yep.
Don't you have a Theorem matrix based on a mass of 5, negative 1, 0 for the top row?
5, negative 1, 0. And I did it like positive 1?
Yeah.
Okay. Oops. Yeah, right. So those should be, yeah, negative 0.5. Any questions about that? Okay. Then the next thing we have to do is deal with expressing moments of inertia in coordinate systems that are rotated from our original one. So let's see. So now we're going to do the second part, which is expressing some moment of inertia IA in a coordinate system with the axes in a different orientation. And the way we're going to do that is with rotation matrices. So the moment of inertia about any arbitrary point A in the new coordinate system is equal to the rotation matrix times the moment of inertia about A expressed in the old coordinate system times the rotation matrix transpose. And again, that looks just like the way we do coordinate system transformations in D form with stress tensors. So let's say that we want to let's say that we have a disk like this. And we want to express that in a coordinate system that's aligned this way. So there's x, y, z. Those all have to be perpendicular to each other. It doesn't really look like it, but and let's say that this angle of rotation is 45 degrees. So what's the mass moment of inertia about the center of mass in this rotated coordinate system? Well, the way we're going to do that is we're going to first calculate it in a non-rotated coordinate system. So first we'll calculate it in the principal coordinate system. And then we'll rotate the coordinate system using rotation matrices. Okay, so if this is the disk, and let's say our principal coordinate system is capital X, Y, Z. Then the mass moment of inertia about the center of mass is equal to, and actually let's give values to this stuff. So let's say that the mass is equal to 1 kilogram, and let's say R is equal to 0.5 meters. So the moment of inertia about the center of mass is 1/2 mass times r squared. That's the x element. What's that? 1/2 times 1/4, so 0.125. That's about the x-axis. About the y-axis, it's 1/4 mr squared. So that's half of this, so 0.0625. And that's also z. So this is in the capital coordinate system. Any questions yet about that? Just finding the moment of inertia matrix about the center of mass in the principal coordinate system. And now we're going to go from this coordinate system to this one. What kind of rotation do we need to do to get from here to here?
Negative 45 degrees about the z-axis.
Yep, perfect. Anyone have any questions about that? So Q is equal to cosine of negative 45, sine of negative 45, 0, and negative sine of negative 45, cosine of negative 45, 0, 0, 0, 1. On D2L in the course materials section, there's a list of programs for TI calculators, and one of them is just a way you can just enter in. You could enter in, if you type this program in, enter in negative 45 degrees about the third axis, and it'll just spit that matrix out to you. So you don't have to keep typing this in every time. So now the moment of inertia about the center of mass in the lowercase coordinate system is equal to Q times the moment of inertia about the center of mass in the capital coordinate system times Q transpose. And can someone calculate that? Okay, 0.09375. Okay. Okay. Like that. And then symmetry gives us these. So what if you need to find the mass moment of inertia about a point A where A isn't the center of mass and the axes aren't principal. Well, first use the parallel axis theorem to calculate the moment of inertia about A with the principal axes. And then second, use Q, I, Q transpose to give IA in desired axes. So just do those two steps. Okay, so now let me give you an example to work on, and I guess I'll do this at the start of class next time. So let's say we have this rectangular, thin rectangular plate. And we want to calculate this about axes that are rotated like this. So there's x, there's y, there's z. These angles are 30 degrees. And let's say the mass is equal to 2 kilograms. The length is equal to 0.1 meter. And the width is equal to 0.05 meters. What's the moment of inertia about the center of mass in the axes shown? Right, we're just doing it about the center of mass.